Welcome to our talk on CVPR, Unsupervised Deep Unrolling Networks for Phase Unwrapping. Phase is crucial for imaging, as it reflects physical properties such as thickness distribution and refractive index. In many imaging systems, true phases are restricted between -pi and +pi, resulting in wrapped phases. Phase unwrapping, PU, aims to recover the original phase from its wrapped version, with broad applications such as depth sensing, fringe projection, INSAR and MRI. Our work focused on noisy wrapped phase images, which is about solving a nonlinear inverse problem, y equals the wrapped version of x plus n, where y, x and n represent the wrapped phase image, true phase image and noise respectively. This task is challenging due to solution ambiguity caused by wrapping and noise corruption caused by n. Conventional PU methods use reliability guidance or specific filters, but their capacities for complex pattern and noise are inferior to supervised learning methods that use paired data for training. Some treat PU as pixel-wise classification and use standard CNNs. They cannot process the phase with wider wrap counts due to fixed number of classes in training. Others map wrapped phase images to the original ones and use RNN-based models, where only limited dependencies can be captured due to cost constraints. These methods are impractical because collecting GT data is costly due to hardware constraint or privacy concern. Unsupervised learning for PU is scarce. One method uses CNN to reparameterize phase image, optimizing its weights to fit the observation. While GT is not required, it needs per sample training, thus slow and unable to learn from external dataset for higher performance. Considering these limitations, can we have a method fast in inference and independent of GT? We show that the answer is yes, and the solution is end-to-end unsupervised deep learning for PU. Our contributions are summarized as proposing the first external unsupervised DL approach for end-to-end PU. We are also the first to explore deep unrolling network for PU, founded on a variational model utilizing wrapped gradients and perceiving outliers. Besides, we developed a recorruption-based self-reconstruction loss leveraging Ito's continuity condition and a self-distillation loss for improved generalization. Our method outperforms existing unsupervised methods and competes well against the supervised ones. Our core idea is to extract the gradients of original phases from different types of points based on their gradient properties, and predict the phases that align with them. First, non-jump points share the same wrap counts, and their gradients remain unchanged after wrapping. Considering their majority, the gradients of their wrapped phases can serve as a noisy version of true gradients, forming the basis of our self-supervised loss. The second type is jump points where the wrap counts differ but the absolute original gradients are less than pi. Wrapping the gradients of their wrapped phases reveals the original phase gradients, which is used for the regularization model. The others introduce extra 2k pi in gradient, referred to as outliers. We defined a variational model based on the gradient equation as follows. A variable E is introduced to absorb the 2k pi residuals caused by outliers. Sparsity is enforced in the regularization module for E. This model is unfolded using proximal accelerated gradient descent, with its parameters predicted by CM module. Based on the model, we built a deep unrolling network called U3net as shown below. The self-reconstruction loss for training has the following doublehead noise injection form to mimic supervised learning. It shows that once we sample U from the distribution of n, training with this loss is equivalent to learning noiseless spatial gradient. For outliers, we introduced an outer wrapping to counteract their impact. The ambiguity of outliers can be reduced by the inductive bias of unrolling CNNs. To address the prediction variance and input misalignment, we proposed a self-distillation loss. It uses earlier predictions for supervising the later training, and wrapped gradient y for input. The total loss function is a weighted sum of those two proposed losses. Here are the evaluation results on two simulated phase datasets. Our method ranked the first in 8 settings with the lightest weight. Here presents a visual comparison of the residual maps on 2 samples, where our method exhibits the smallest residuals. We also evaluated on INSAR data. Our method achieved the best in both quantity and visual quality. We performed ablation analysis as shown below. The left shows that the outer wrapping in the loss is crucial and the recorruption mechanism effectively suppresses noise, while the right indicates that the outliers are well perceived. To conclude, we propose the first end-to-end unsupervised learning method for PU, overcoming the dependency on GT and time inefficiency. We developed a deep unrolling network that utilizes gradient and perceives outliers, as well as a self-reconstruction loss supplemented by a self-distillation loss to enhance generalization ability. In future, we will explore more efficient perceiving schemes for outliers, and enhance the model robustness to noise inconsistency. That's all. Thanks for your attention.